So recall that we've been really focusing quite a lot on linear differential equations. In the first order case of linear differential equations, we gave a fairly comprehensive picture for how to solve these through something called the method of integrating factors. And I'm hoping that that phrase just blossoms that theory inside of your mind. Then we moved on to thinking about second order equations. We talked about things like the superposition principle, which I'll reiterate here, and the existence and uniqueness of solutions for second order equations. But we very quickly narrowed our focus to the second order homogeneous linear differential equation with constant coefficients. It's a lot of adjectives there. But it was kind of necessary to do that because the general theory is fairly difficult, right? And people spend their lives thinking about this sort of thing. Nonetheless, it was worthwhile to narrow our focus like that because it allowed us to understand the harmonic oscillator. At least the harmonic oscillator in the case where there was no what's called external forcing function. But we do want to understand how a physical system like a harmonic oscillator behaves when it is exposed to some kind of forcing. For example, and I hope that we'll have the time to elaborate on this example, imagine that you have a water tower sitting atop the earth, okay? And you have a whole bunch of that mass accumulated in the tank of the water tower, which is above ground. I don't know if you've ever seen a water tower. They're ubiquitous in my hometown of Davis. Anyway, imagine that water tower is subject to an earthquake, so there's shaking. Then the tank is going to be subject to some serious external forcing. And what we would like to understand is how this system, which we can model with a harmonic oscillator, will behave under this external forcing function. This is very important for like safety and design considerations when we're thinking about something like a water tower. So it's something that we definitely want to take into account. But we'll get into all of that. For here, in this video, I want to talk about non-homogeneous linear differential equations in general, and think about how the linearity of the differential equation will give us a strategy for solving non-homogeneous linear differential equations fully. Of course, we'll figure out what we need to do in order to really make that happen for any particular case. But the theory here is quite nice. So let's get into it. So let's talk about non-homogeneous linear differential equations. So what is such an equation? It's going to be something that looks like this: a sub n times the nth derivative of y. Now I'm thinking of these a's. They're going to be my coefficients in my differential equation here. I'm going to think of them as being functions here, fully linear, right? So they're functions of x only, plus another function of x, which I'll call a sub n minus 1. This, and we'll go all the way down to a1y prime plus a naught y. Remember, y is the zeroth derivative of y. And this will be equal to f of x. Now, recall that this adjective, homogeneous, is applied to our differential equation when f of x is 0. So if this thing here is 0, or let me say if 0, then we say homogeneous. And if not 0, then non-homogeneous. Yeah? Hopefully that's clear. The other thing that I want to do here, just because this is a lot of stuff to write all at once, just to simplify our way of thinking about it, is to declare that this whole side here, this left-hand side, is really some linear operator, which I'm going to call L, applied to the function y. L is what's called a linear differential operator. Fancy words. It's linear when it is able to be written with this particular structure. And it's an operator, well, it's a differential operator, differential because it involves derivatives. And it's an operator because it's a thing which eats functions and spits out functions. That's an operator. This is what we call an order n differential operator. Okay? I hope for obvious reasons. Now, let me review some of the crucial facts about equations like this. The first is called the superposition principle. I'll call this superposition. And this has to do with what happens when L eats a certain type of sum. L of y C1y1, oh yeah, C1y1 plus C2y2 is equal to C1L of y1 plus C2L of y2. Okay? This is just a routine check. Okay, you can check this for yourself by shoving C1y1 plus C2y2 into this definition for L of y. And if you do that and you do use various properties of the derivative, this will fall out. This right-hand side here will fall out. Okay? This is a very important principle. We're going to use it to the hilt today. And you're going to see that this is what lies at the heart of the linearity of this differential operator. The reason why it's so appealing and wonderful is precisely because of this superposition property. The second thing that I want to say is about existence and uniqueness. Now, you might recall that this was, when we first discussed this was framed in terms of solutions to the initial value problem, right? When you take an equation like L of y equals f of x, and you pair it with a collection of n initial values, and remember what that means. That means that you pick a particular point x naught on which all of the coefficients are continuous or something like this, and then and then what you come up with is a unique solution to that initial value problem. But if you think of those n initial conditions as being n constraints on your solution, then I think a better way, not a better way, an equivalent way of thinking about it, the one that I want you to think about here and now, is that the following: the solution space to the equation L of y equals f of x is n-dimensional. And maybe I should say, under very mild assumptions. So first of all, what do I mean by the solution space? I mean the set of all functions, y, which satisfy this differential equation. It's an n-dimensional space. What do I mean by that? I mean that you sort of have n different... Oh, okay, here's a better way. It sort of means that in the general solution that there are going to be sort of n degrees of freedom that you get to turn the knobs on and still generate solutions as you adjust those knobs. What do those knobs look like when you actually write down your solution? They look like those constants that we've been calling C1 and C2, etc. Right? Those constants, which are arbitrary constants that you can set to be whatever you want to set them to while still remaining solutions, Those are the degrees of freedom which represent different directions in the space of solutions here. Now, how do you write down these, or how do you describe the solution space, this n-dimensional solution space? Well, this is where we want to think a little bit about how these ideas come together. So here's some terminology, definition. So given this non-homogeneous equation, given L of y equals f of x, as above, we're going to call the associated homogeneous equation. So I'm defining for you this notion. Associated homogeneous equation is simply L of y equals 0. Okay? So it's just where you zero out the f of x altogether. And here the idea is that what we do to find the general solution in the homogeneous case, to find the general solution to this, what we do is we hunt down n linearly independent solutions. Let me call them y1, y2, all the way up to yn. So we have n, each of these are solutions to the differential equation L of y equals 0. Crucially, that equation is homogeneous. Now notice that by superposition, we can make the following calculation. If I take a superposition of these n solutions, so if I look at L of C1 y1 plus C2 y2 all the way up to Cn yn, these C's here, I should say, these C's are constants, okay? Then this is equal to C1 by the superposition principle up here. By the superposition that we've got sitting right here. This is equal to C1L of y1 plus C2L of y2 all the way up to CNL of yn. Oh. But don't lose sight of what these y's are. What are these y's by assumption? These are solutions, and maybe I should be clearer, these are linearly independent solutions to L of y equals 0. We know such exist. Okay, and that's by the existence and uniqueness theorem. Because the space of solutions is n-dimensional, we know we can find these n linearly independent solutions. Remember, linear independence means, again, that or it means that these n solutions kind of point in different directions. The space that we live in is three-dimensional. And that's because there's sort of three independent directions. There's up, down, for example, forward and backwards, and left and right, or right and left. And those are three independent directions. What I'm saying is that for an order n linear differential equation, the solution space is n-dimensional, meaning that I can find n different solutions which point in n different directions in some sense. Okay? And if they all point in different directions, then when I take the general superposition of those, I'm going to fill out an n-dimensional space of solutions. Okay. But now, what I'm saying is the y in purple here, y1 through yn are solutions to the associated homogeneous equation, L of y equals 0. But now, if that's the case, what is true about this, and that? All of those are 0. Because after all, y1 is a solution to L of y equals 0. y2 is a solution to L of y equals 0. So all of those are equal to 0. I hope that's clear. So in other words, this whole thing here is C1 times 0 plus C2 times 0 plus Cn times 0. It's all 0. So it's again a solution. That's the point. So an arbitrary superposition of these n solutions is again a solution to the homogeneous equation. Okay? So these y1 through yn map out for us this, or carve out for us n directions, independent directions in the solution space. Now, let's call this general solution to the associated homogeneous equation, to L of y equals 0. Let's call this y sub h. So this is going to be C1y1 plus C2y2 plus CnYn. Right. In other words, this whole thing right here is, I'm going to call that y sub h. Okay? Then, the next ingredient that we want here is what we're going to call a particular solution, y sub p. Let y sub p... Oh, wait, I'm realizing maybe I'm a little bit out of step with how the book does it. Let me just check their notation. Yeah, they call it a little bit differently. Sorry. Let's call this y sub c, because I'm realizing I'm a little bit out of step. This is actually called in the textbook y sub c. Sorry. Let's not call it y sub h. Let's call it y sub c. Y sub c stands for what's called the complementary solution. Okay? But then y sub p is going to be any particular solution to the actual equation. Okay? So let y sub p be any particular solution to L of y equals f of x. Then please notice by superposition again, if we take y sub p and we add it to y sub h, y sub c, keep calling it y sub h because I think in my head homogeneous, y sub c, the complementary solution. If we take y sub c and we add to that y sub p, the feeling I want you to feel, y sub c is a space, and we're going to take that space and we're going to translate it by y sub p. And what we're going to obtain is still n-dimensional, but observe. If we take L of y sub p plus y sub c, by superposition, this is equal to L of y sub p plus L of y sub c. But what do we know about L of y sub c? It's 0. You see that, right? L of y sub c is 0. Look, L of y sub c is equal to 0. So this is equal to simply L of yp. And what is y sub p by definition? It is a solution. It is a solution to L of y equals f of x. So L of y sub p is equal to f of x. What am I saying? I'm saying that here, this is a solution to L of y equals f of x. Okay? And I want you to notice that it's n-dimensional because this is n-dimensional. I've taken this n-dimensional thing and I've just moved it by y sub p to get another n-dimensional thing over here. Okay? This is the idea. So to solve a linear differential equation, non-homogeneous, here's the bottom line. Non-homogeneous linear differential equation. Find the general solution. 2 steps. 1. Find the general solution to the associated homogeneous equation. Which is L of y equals 0. Solve that and call it y sub p. No, I'm sorry. Call it y sub c. And then 2, find a particular solution. Call that y sub p. Okay? Shoot, I should have, let me fix this because I need to write. Let me move this guy over a little and then give myself space here to write y sub c. Okay. Then the general solution to L of y equals f of x is y equals y sub c plus y sub p. It's this n-dimensional thing moved, translated by y sub p. Okay? All right. In the next one, we'll learn how to find y sub p, right? Because that's the open question. And we're going to see that the method we're going to learn about is just basically an educated guess. Okay? We're going to learn how to do that educated guess. And then we'll do some examples. All right. See you in the next one.